start recording. Okay. In order to practice for it, you will want to study 3.1e. And some of the questions are different than other questions, so go through the whole thing, okay? And 3.1f. So 3.1e gives you qualitative analysis questions. 3.1f is more about which things are electrolytes. Can you write the dissociation equation? Can you write the dispersal equation? What ions might be present if you got a precipitate? So you're gonna need to use your table for that. There's a few other types of questions. It just gives you a variety. I discovered, though, that many people in my last block did not know the meaning of the word miscellaneous. Have you guys heard of the word miscellaneous?
Yeah. Yes.
2 people have, but I'm betting that a whole bunch of other people haven't, especially if English is your second or third or however many language. Miscellaneous just means a bunch of this and that. Yes? Stuff. Stuff from here, stuff from there, stuff from everywhere. Okay? A bit of this. A bit of that. A bit of the other. Not that you need to know that for chemistry, but you will hear the word miscellaneous. You will hear the word sometimes in your life, so it might be nice to know. And sometimes you'll just see people abbreviate it because it's a really long word. They'll just say MISC, and that stands for miscellaneous. Okay, English language lesson done for the day. We are going to be looking at 3.2a. Is there anyone who did not get a copy of this handout? Everyone got one? Here's why you're getting it. It is in your workbook, but the pages are not lined up correctly. So it's like the top of page 3 is at the bottom of page 4, and then it cuts in half, and it's just not good. So that's why I think there's one on your desk already. Yep. Yeah. Okay. So, is there? Yes, there is. So, yeah, that's why you have a new copy of it. And in fact, that reminds me, I need to print the good copy onto OneNote. Print. Print. Current section. Okay. There we go. All right. Now we're going to watch a little video up to 3:06 only. And this is Professor Dave, and then we're going to talk it through. So just watch the video. Don't worry about writing anything down. We're going to go through the sheet itself in just a bit. So let's hop on over here and watch Professor Dave talk about the solubility product constant.
Professor Dave here. Let's talk solubility.
He knows a lot about the science stuff. Professor Dave explains.
Woo.
When we first discussed solubility, we learned that some ionic compounds are water-soluble and will completely disperse in solution due to the ion-dipole interactions they will make with water molecules. We also learned that other ionic compounds are water-insoluble and will not dissolve at all, remaining completely in the solid phase. Beyond this, if the components of such a compound find each other in solution, they will precipitate.
So that's like when we have a double replacement reaction, and let's say This ion finds that ion and they precipitate.
And leave solution completely to form a solid. This is actually a slight oversimplification that served its purpose at the moment, but now it's time to get a more sophisticated and quantitative understanding of solubility. So let's get a closer look. It's true that many ionic compounds are completely soluble, but the reality is that even the ones that we call insoluble will dissolve to a minuscule degree. Whatever the degree to which dissolution occurs for a particular substance, we can communicate this using the solubility product, abbreviated as KSP.
Guess what it is?
The constant of a soluble product.
It is the KEQ for a slightly soluble or like very low solubility solid in solution.
Let's look at a substance like silver chloride, which we label as water insoluble. As we said, if there is an excess of it in water, it will dissolve to a tiny extent and cause a dynamic equilibrium. Some ions dissolve as other ions rejoin the lattice. Just as with any other type of equilibrium, there must be an equilibrium constant to describe it, and that's the solubility product. As we might guess, this will simply be equal to the product of the two ion concentrations.
Now, why do we not include the solid?
So we do not count solid in KEQ.
We do not count solid in KEQ because they don't have a meaningful concentration. It's not something you can change.
In solution, each raised to the power of their stoichiometric coefficients, which in this case is simply 1 and 1. Notice that we do not include the solid itself in this expression, as we do not include solids in equilibrium expressions. The smaller the constant, the fewer the ions that will be present in solution.
So if we have a smaller constant, so if this value here is small, what he's saying is that means that the ion concentrations must also be small. And if this is small, what does that tell you about how much dissolves?
Not a lot.
Not a lot. So the smaller the ion concentration, the lower the solubility, the less will dissolve. Okay?
And therefore, the less soluble the substance must be. And compounds that are extremely water insoluble will have KSP values on the order of 10 to the negative 30, negative 50, or even smaller. Let's make sure we can write these solubility products for various equilibria. Take something like calcium carbonate. First, we must write out the complete equilibrium. Upon dissociating, this will form a calcium ion and a carbonate ion. Therefore, the solubility product will be equal to the product of these two ion concentrations. If we have something like magnesium hydroxide, it's the same thing, except that dissociation produces one magnesium ion and two hydroxide ions, which means that hydroxide ion concentration will be squared in the solubility product expression.
All right. And we're just going to leave it there for now because we're never going to see a compound like that in Chemistry 12. If you're interested,
we can even do this for something more complicated, like apatite, which is a mineral. This will dissociate into 5 calcium ions, 3 phosphate ions, and a hydroxide ion. So the solubility product expression will look like this.
But like I said, we won't be looking at those in Chemistry 12. And in fact, that's as far as we're going to go today. Okay. So we're going to then go to this little handout that we got. Did everyone get one? Yes, good. All right. So solubility, this is a temporary definition. We're going to replace it with a better definition later. It is the degree to which a solute will dissolve in solution. How good is it at dissolving? It's its soluble ability. The solubility. Huh. So, this is just what Professor Dave was talking about at the beginning. If something is water soluble, it will dissociate. And forms into individual ions. Other ionic compounds have been known to be insoluble and they will not dissolve in water and they remain in the solid phase. So if we have things that are water insoluble, it just sits there. You dump it in, nothing happens. Now, if you were to put in something like Ag plus and Cl minus, they would get together and form a precipitate. So insoluble salts will precipitate if you put the component ions in there. Okay, so if you were to mix some silver with some chloride, you will get a precipitate. And the precipitate is the solid. Now, this whole business of it being completely insoluble, that is an oversimplification. Even the most insoluble compounds will dissolve to a very small degree. But most of it stays solid. That is why on your solubility table, does it say insoluble? What does it say? Low solubility. So this here would be low solubility because it's not that it doesn't dissolve at all. It just dissolves only a little teeny tiny bit. Something like 10 to the negative 15 molar. Okay? Like 0. Or smaller. That would be the concentration. Yes? Tiny concentration. All right. The degree to which a substance dissolves can be communicated by its solubility product constant, which is also known as the KSP. Solubility product constant is not the same as solubility. They are related to one another, but they are not the same. I'm going to keep saying that because it is one of the things that people mess up the most. And I'll tell you why. It's because if we go to our data pages and we look on page 5, it says solubility product constants at 25 degrees Celsius. And people see that word solubility and they think, oh, that's the solubility. And in a multiple choice question, it'll say, what is the solubility of barium carbonate? And one of the options will be 2.6 times 10 to the negative 9. And that will be wrong. Because although it is related to that value, the solubility is not 2.6 times 10 to the negative 9. The solubility product is 2.6 times 10 to the negative 9. But they sound similar, so it's easy to mix them up. Okay? When we start doing problems with that, I will remind you that these two things are not the same. Okay? However, for now, we don't have to worry about it too much. So here is an insoluble salt, AgCl. Some ions will dissolve. This is the forward reaction. This is dissolving. Other ions rejoin the crystal lattice. This is known as, and I'm going to start way over because it's a long word, recrystallization. We are recrystallizing. And that is the reverse reaction. And these two processes occur at the same time. And if they're occurring at the same time and at the same rate, what do we call that? A dynamic equilibrium. I'm just going to write EQM for equilibrium because there's not enough space. And so if every time one particle dissolves, another particle recrystallizes or precipitates, what will happen to the concentration? It will stay the same, okay? And that maps with what we know about concentration because concentration is what kind of a property? A macroscopic property. So concentration, which is a macroscopic property, remains the same. And that's how we know we are at equilibrium. What is a macroscopic property? An observable property. Okay, and this is the page where if you were to look in your workbook, you would see that like it gets cut off. It's really ugly. 3.2a. Here. This is what it looks like in your workbook. It's like half on the wrong page and then it's cut off. It's just bad, which is why I provided you with this redo of this particular section. Okay, so our solubility product. Remember, this is not the same as solubility. Yes, take the good copy. So we've written this is our solubility equilibrium equation. That's what we call it, our solubility equilibrium equation. And we're going to use this so often that I'm going to start abbreviating it as the SEE, the solubility equilibrium equation, or the C. And you'll notice that the solid is on which side? Left or right? Solid is on the left. And the reason it has to go on the left is because it needs to be consistent. What you do needs to be the same as what some student over on the other side of Canada is doing, because we're all going to be using the same data tables, like this one. Yes? And this is the value that you get if you write the solid on the left. If you wrote the solid on the right, you would end up with 1 over 2.6 times 10 to the negative 9. Okay, and so that's not what we are given in our tables, so we need to make sure we put the solid on the left. I think you guys are pretty good at writing KEQ expressions these days. Yes, you've had lots of practice. So writing it here, the only thing to remember is do not include the solid. KSP is what we call it, stands for solubility product. We do not include solids. And let's just take a look and see why we don't write the solid on the right. We don't write the solid on the right because that would put our ion concentrations in the denominator. And it would make for somewhat harder math. I mean, it's not that hard, but it's a little bit harder, yes? Right? You have to, take a reciprocal and do things. It's just more work. So let's not do more work. All right, and we're going to take an interlude here. This is one of the most common student errors, and I'm going to talk about it all through this unit, so hopefully you will not make this error. Do you remember what I called the solubility equilibrium equation? We called that the C, the S-E-E. And the key thing about the equilibrium is that it is an equilibrium. So what kind of arrow do you think you will use?
Double arrow.
You'll use the
Double
double
arrow.
arrow. Okay? Now, a precipitation equation. What is the product of a precipitation reaction? And this is not a hard question. This is meant to be easy. The solid is the product. And do you remember what we wrote on where we wrote the solid in the solubility equilibrium equation?
On the left.
We wrote the solid on the left. In a precipitation equation, the solid is the product. So where should we write it? We should write it on the right. So we're going to have our solid. And we can call the precipitation equation the PE, precipitation equation. So we have the C and the PE. And you will use these in different contexts. So some problems, we good? Okay. In some problems, you will want to use the C. Okay, the solubility equilibrium equation. And what is it used for? How do you know that you'll want to use it? You will use it in KSP. When you see the term KSP, you will use it when you see the term solubility. You will use it often when you see the word saturated solution. So those are the words you are looking for that will let you know that you want to use the solubility equilibrium equation. When you write a precipitation reaction, We are forming the precipitate. The solid goes on the right. What kind of questions use the precipitation reaction? Well, if they ask you for the net ionic reaction between two solutions, so that would be like a double replacement. Or when you're doing a titration. Or when you see the word precipitate. So those are the key things you're looking for when you're looking for a precipitation equation. So usually, with solubility equilibrium equation, we're worried about how much is dissolved. Yes? How much is dissolved? When we're looking at a precipitation reaction, we're worried about how much product is formed. How much are we using up? Yes? So, precipitation, we will be later on, and this gets really confusing for people sometimes because they're like, I don't know which to use. Maybe we mix two solutions, a precipitate forms, and then we want to know about the solubility equilibrium equation. That will happen later, okay? Later, not now, later. You have to choose the right equation, make it go in the correct direction, the solid on the correct side, and use the correct arrow, either a one-way for precipitation or a two-way for the solubility equilibrium equation. Now, what we're going to do here is we are going to choose the correct type of reaction. So, read the question and think to yourself, am I thinking about the precipitation? Or am I going to want to use the solubility equilibrium equation? So take a read through number 1 and number 2 and see if you can choose whether you use the PE or the SEE. Discuss with your partner. So in the first one, are we forming the precipitate or are we wondering how much is dissolved? We're forming the precipitate, so what should we be using? The PE. Could you guys, would you be able to write, without writing the complete ionic equation and the formula equation, could you go straight to the net ionic equation?
Yes.
Give it a try.
What? You took my last one.
What do we know about ammonium?
is soluble as everything.
Ammonium is soluble with everything, yes. So will it be in the net ionic equation?
No.
No. Well, what am I doing? I'm a daft girl. That's okay. So the NH4 would try and get together with the chloride, but it won't form a precipitate. Who will form the precipitate? BaNSO4. You can check on that. You can go to your data pages, to the solubility table, and say, I've got SO4 and Ba, and that is low solubility, so that will be the precipitate. So if you've not already written it, you know that barium and sulfate will form the precipitate. Please write that precipitation equation, the net ionic equation. Now, one thing I'll make clear here is that in this unit, your states are important. And that's because most of the time we're like, oh, is it aqueous or is it solid? So you need to write when it is aqueous and when it is solid, okay? Do I use an equilibrium arrow here or do I use a one-way arrow? One-way. Excellent. What words are clues to what we use in question 2, in example 2?
Solubility.
Solubility and KSP. Those both tell you that we should be using the solubility equilibrium equation. Could you please write the solubility equilibrium equation for lead iodide, PbI2? All right. Would you guys like to learn how to do this question right now? I bet you can, because you've done KA questions, yes? Yeah?
Yeah.
And so if this was a KA question, now maybe what we should do is we should make sure that everybody has paper, because there is not enough room to do a KA question on this piece of paper, so there is not enough room to do a solubility product, a KSP question. So make sure you have a piece of paper. I'm going to copy my solubility equilibrium equation over here.
I'll take my paper back and bring that. I thought you did.
And we are told that the molar solubility Huh?
I was gonna ask, in the equation, why is it not I2? It's iodide.
Ah, okay. So iodide has an extra electron. Where did it get that? It got it from PB, yes?
Yes.
So we have iodide, and it has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7, and it gained an extra electron from the lead, and so it has a full shell. Yes, whereas that is iodide, whereas iodine is neutral. And that is because one iodine, 1, 2, 3, 4, 5, 6, 7, pairs up with another iodine, 1, 2, 3, 4, 5, 6, 7. Nobody has gained, nobody has lost. Everybody's neutral. That is I2. But if you have the ion, it's just single. Does that make sense? Cool. All right. And we are told that the molar solubility of PbI2 is, and I'm going to cheat and I'm going to simplify it a little bit because I don't want to write out like 3 digits. I'm just going to call it 1.5 times 10 to the minus 3. Are we okay with that? Okay, so we're just going to call it 1.5 times 10 to the negative 3 molar. And we are also told that the KSP, no, we want to calculate the KSP. If this were an acid question, what would you do? Race table. Ah, excellent. Now, this is a molarity. What does molarity measure? Molarity measures concentration. Yes?
Yeah.
So what do we know the concentration of? PbI2 is a solid, but do you remember when we had an acid, even when it was like HCl and HCl completely dissociated, I would say I have 1 molar HCl.
Yeah.
Even though there's not really actually any HCl in the water.
Oh, yeah.
Yes. So this is very similar. Even though there is no solid PbI2 in the water, we say that the concentration of lead iodide is 1.5 times 10 to the minus 3 molar. But I'm going to put it in brackets because do I really have that much solid concentration? No, because solids don't have a concentration. But that's how much I dissolved into 1 liter. I dissolved 1.5 times 10 to the negative 3 moles in 1 liter. How much lead do I start with? How much lead is dissociated in the very instant when it hits the water?
0.
None. 0, 0. Now, how much dissolves? This much dissolves. 1.5 times 10 to the minus 3 molar. 1.5 times 10 to the minus 3 molar. Oh, except for I have a coefficient. So what do I need to do? Times 2. And this is minus 1.5 times 10 to the minus 3 molar, which ends up being nothing anyway because we never had a solid to start with. Okay, well, we did have a solid to start with, but we didn't have any actually dissolved. So what do we end up with? We end up with 1.5 times 10 to the minus 3 molar and 1.5. Nope, sorry, 3.0 because I forgot to multiply by 2. 3.0 times 10 to the negative 3 molar. Now, this seems like a lot of work for a rice table where the solid doesn't actually work properly. Yes? So you can simplify this. We don't actually have to do all of this. We could just say, I know that I have 1.5 times 10 to the negative 3 molar lead iodide. That means that when it dissociates, I have 1.5 times 10 to the negative 3 molar lead. And I have 2 times 1.5 times 10 to the minus 3 molar I2, which is 3.0 times 10 to the negative 3 molar. So you don't have to write out a whole rice table because it's not really applicable here anyway. Do we like this better? It's a little bit of a shortcut. Does it make sense? If your concentration of, yes. So what this is doing is it is saying when it says the solubility is 1.5 times 10 to the minus 3 molar, that is how much dissolves. Solubility is how much dissolves. I should have said that at the start. Does that make more sense if I tell you solubility is the amount that dissolves? In moles per liter. So this right here is our solubility. That's how much dissolves. And for every one of those that dissolves, I get 1 lead. And for every 1 PbI2, I get 2 I minus. Does that make more sense now? Okay, good. Thank you for asking that lovely clarifying question. I appreciate it. Sometimes I get ahead of myself. Now, if we know the concentration of this ion and that ion, and remember, what were we asked to find? We were asked to calculate the KSP. What might we do next? We might write the KSP expression, yes? Because you can't calculate a KSP unless you have a KSP expression. Please write the KSP expression for our reaction there. And you guys get to critique my KSP expression. Tell me what you like about it, what you don't like about it. Mainly tell me what you don't like. We do not like that coefficient inside the bracket. Get rid of that, and it should instead be squared. Are we now able to calculate KSP? Yeah, because we got the ion concentrations, just toss them in. 1.5 times 10 to the negative 3 times 3.0 times 10 to the negative 3 squared. And we get, I had a calculator, but I don't know where it is. So we have 1.5 e 3 negative times 3e 3 negative squared equals 1.35 times 10 to the negative 8. Am I done? You should always check your answers for sig figs. How many here? 2. How many here? 2. So I want to have 2 sig figs, so that's going to become 1.4 times 10 to the negative 8. And you see, you thought you didn't know how to do this new type of question because it was brand new. Did you know how to do it? Kind of mostly, right? Because it's very, very similar to Ka, okay? Just this little bit here is a little bit different, okay? Instead of using a race table, we can just separate the ions. All right, next. Actually, before we do this next one, I would like you to go walk around for 5 minutes, go outside where it's nice and where you won't bother other classes, okay? Don't wander in the hallways, don't visit other classes, don't make noise. Just go outside and wake yourselves up. Up you go, out you go, out, out, out. 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 Go breathe some air. Air. No. Out. It doesn't. Oh yeah, you can pop me down. You don't need to go. Up you go. Back.
That's not right.
You went outside. Okay. All right. Are you ready to go? Okay. You guys make me feel like I'm a horrible ogre for forcing you to go out into the beautiful, beautiful spring weather we are having. I know I'm a terrible, terrible person. Terrible. All right. Let's take a look at this one here. We have a sample of well water. A student titrates 10 milliliter sample of well water with 11.97 milliliters of 0.100 molar AgNO3 to precipitate the chloride ion in the well water. What is the concentration of chloride? Are we going to use the C or the PE? Do you guys agree? Precipitation equation, because whenever we're doing a titration, we're more concerned about like the precipitation. Okay, so we're going to use the precipitation equation. Now, this one sometimes is confusing to people because we are given AgNO3 and we are given Cl minus. However, you guys are grade 12 students now. So the fact that I've given you AgNO3 and Cl minus should not prevent you from writing a net ionic equation. Could you write a net ionic equation? Did you guys go outside?
Yeah.
Are you lying to me?
No.
Okay. You sure?
I'm sure not.
Okay. Jonathan, are you sure? Okay. All right. What do you guys know about nitrate ions? They're soluble with everything. So what does that mean that nitrate is? Nitrate is a spectator ion. And if we're writing the precipitation equation, where should the solid go?
On the right.
On the right. Who is the solid? Tell your partner, who is the solid?
I don't think it's on everything, right?
You don't have very many choices, do you? You have three ions. You have Ag plus, you have NO3 minus, and you have Cl minus. Who's going to be the solid? Ag and Cl, because NO3 is soluble with everything. So we're going to have AgCl over here. And we're going to have Ag and Cl over here. And you guys are going to critique my equation. States, thank you. Now, you guys just did a titration lab and you just did some titration problems. Do you remember how a titration works? I'm betting that you don't because my other block didn't. How many people think they could solve this? Maybe, probably, maybe. I got one. I got one person who could probably solve it. Anyone else? Two. I got two.
I could try.
I got three. Four. For those of you who have forgotten, titration is just applied stoichiometry. And what is at the heart of stoichiometry?
Mole ratio.
Mole ratio. That's supposed to be a heart. It's sad. Let's fix that. The first half was okay. There, that's better. At the heart of stoichiometry is the mole ratio. Now, what that means is that you are going to need to take your known, and you're going to have some units, and you're going to have to convert it into what? What's at the heart of stoichiometry? Moles. So you're going to convert it into moles of your known substance. Now, a mole ratio is a ratio because you've got moles and you have moles. So the middle step is always moles to moles. Stoichiometry, always moles to moles. And what will we be finding here? Moles of the unknown. So this part here will be the same in every stoichiometry problem you ever do. Okay, you'll go from moles to moles. And then, unless they've asked you for moles, in which case you're done, you'll convert to whatever they want you to find about the unknown. So I would like you to look at this question and decide who is the known.
A, B, and O.
You have to stop saying everything out loud, Isaiah. I need other people to think too. Who is the known? How did Isaiah know it was AgNO3? What does it tell you about the AgNO3? It tells you both the molarity, which is moles per liter, yes? What else does it tell you? It also tells you the milliliters. Are you able to take milliliters and moles per liter and find moles? Yes, that's why it's your known substance, because you have enough information to find the moles. Please do that. Find the moles of AgNO3. We will use the 10 milliliters. It's the well water. It's the unknown. Whoop. I'm sorry, I wrote the wrong equation up here. That should be a Cl. What is step 1 of stoichiometry? Always find the moles of the known substance. What do you know about the moles of AgNO3 and the moles of Ag? You don't know anything about it? How many Ags are in AgNO3? One. So if you know the moles of AgNO3, you know the moles of equals moles of Ag plus. So those are the moles of the known. Second step in stoichiometry, you always find the moles of the unknown. I'm just going to call it UNC. Okay, UNC. Who is our unknown here?
Cl minus.
Chloride. Okay, so we want to find moles of chloride. How do we go from moles of one thing to moles of the other thing? We use the mole ratio. Where do we find the mole ratio? In the balanced equation. And then finally, what are we asked for? We want the concentration of Cl minus. What is concentration measured in? Moles. So we want the moles of Cl minus over the liters of the Cl minus solution. Do you think you could solve it now? Yes? Go for it. Do it. If you've not already done it. It looks too far off. I'm just guessing because the volumes are fairly similar, yes? And it's 1-to-1 for ratio. So shouldn't the concentrations also be similar? I mean, I could be wrong.
Oh my god, I should be wrong. I know what it is. Yeah.
That's the issue. You know why? Because we want the concentration of chloride. Do I want the concentration of chloride in my final concentration mixture? Or do I want to know the concentration of chloride in the 10 milliliter sample of water? Yes? Good.
It's not how you want this one. I just wrote it. That's concentration of CF.
So the first thing I'm going to do. Oh, no, that's cool.
Oh, dear.
Ah, okay. And then we did this. Okay. Okay, then we got this.
Wow. Oh, wait, that's one factor. Wow.
Okay.
I'll have
Now
you
you
going.
have
I think the last time. Yeah, at least that's 5%. That's 10%.
Okay. Now we have this. Not polarity of
Well, at least now they're.
Do you need the whole supply?
Those other supports are counteracting.
Use a 10 milliliter sample blow. Yes. Yes. No problem.
Average is too cheap. I thought.
What are these units?
Great. Great. No.
So you can multiply the meters. We divide by meters, so they multiply by the square. Oops. I understand. He does that sort of thing too at the end of the day. He says, what's happening? You look, this looks better. Okay. All right. And the only thing here is that this reading is done.
Okay, I don't even. Really? Like, okay, I know I got at least.
11.9.
No, I didn't do anything.
Anyway, end of the day, right? So let's pretend you.
I didn't.
Right? This would be correct. Okay? If you look at that number, you'll think, wow, that's way bigger than I usually see it. And I say to yourself, oh, I'm going to be like there. Like that, it works. Okay? Concentration of chloride. Yes, and how many milliliters of plus? How many? Well one. And the one is well one. Yeah. I'm noticing everyone has end of the day brain. So go home, solve this, we'll look at next day. Cancel homework, finish the titration question. Study for your 3.1 Qs, that's your only real homework. Okay? 3.1E and 3.1F, you're on Thursday.